The dynamic system we are considering is a rocket during flight. We want to observe the maximum altitude the rocket will achieve, so we will not be considering anything that occurs after apogee has been reached. For simplicity's sake, the system has been reduced to a cylinder with mass m and a constant drag coefficient. We are also assuming that we are launching in ideal conditions. This means there's no wind and no horizontal forces acting on the rocket at any time. Finally, we are assuming that the altitude range this rocket is traveling is low enough that the density of air and acceleration due to gravity are constant.
Now moving on, here we have our free body diagram. All the forces as shown are acting through the center of gravity. Our rocket is accelerating upwards due to the thrust, which opposes the weight and the drag as shown here. On the right, we have our coordinate system. This is very similar to the one used in ICGE 3. However, here the inertial and the body axis have been overlapped for simplicity's sake, as the rocket is assumed to only be accelerating upwards, in our case in the positive z direction.
There are two different equations for both acceleration and mass flow rate. This is to represent the two different phases of flight. First is the burn phase when thrust is acting on the rocket. This is followed by the coast phase when the motor has burnt out and there is no thrust being applied. By rewriting the governing equations into their state space forms, we can use numerical integration to find the states of the system at any time. The following assumptions have been made. Coefficient of drag, gravitational acceleration, density of air, and cross-sectional area are constant at all times. Thrust is assumed to be instantaneous and applied constantly during t. M changes linearly with time, so m dot is constant during t. After t amount of time, the acceleration and m dot equations switch to their coast phase equations. Here is an altitude versus time graph of the rocket shown at the beginning of this video.
So here we have our block diagram for our rocket system. Here we have the inputs as T of t, which stands for thrust, which changes with respect to time. And then we have our transfer function here, which describes how the inputs and outputs are related through some process or calculation. In this case, it is dictated by our governing equations. And then we have our outputs, which are displacement, velocity, and acceleration respectively, and also our mass output, which changes with time because of the fuel burned.